Okay, we're ready for the last talk of the session. So this is Lasse Wolff on a fundamental limit on the power of entanglement assistance in quantum communication.
Yes, so thank you, and thank you all for coming. I'll talk about a new, or really the first fundamental limit on the power of entanglement assistance in quantum communication. And this is based on this paper you see here, which is available open access on the PRL website or an archive. And it's joint work with Paula Belzig, who's somewhere in the audience, and Marco, who's right here, and also Matthias Christandl and Bergfinnur Durhuus. Okay, so I'll just cut straight to the chase. The problem we're trying to answer is this fundamental question about how large can this ratio of the entanglement-assisted classical capacity over the ordinary classical capacity of a quantum channel get. And the new result I'll present here is the fact that we have proven now for the first time really a new bound on this ratio, and I'll spend the remainder of the talk briefly going through the proof techniques used in the proof. Right. So before delving into the discussion, we should define what exactly it is we're talking about. So the classical capacity of a quantum channel, C of t, is defined like this, and the entanglement-assisted capacity, CE of t. You can also see the expression here. And I guess if you haven't really seen these expressions before, you probably need a couple of times to get used to them, and they're perhaps not too enlightening. But the main idea is that for both capacities, we are trying to calculate the optimal ratio m over n, where m is the number of ideal bit transmission channels. You can use quantum channels, which are encoders and decoders, to simulate by using n copies of your original channel T. So it's like basically how many classical bits can you transmit through your channel with or without the use of entanglement. And the only difference between C and CE, so the entanglement assisted and the ordinary capacities, is that in the entanglement assistant case, you allow for a bipartite entangled state to be shared between sender and receiver before the transmission. So this allows the encoder to act on one part of row and the decoder to act on another part of row. And this will in general boost the rate of bit transmission, or the communication rate of the channel. Okay, so let's look at this ratio for some examples of channels. So for example, for the k-dimensional identity channel, this ratio is 2. This is, if you think about it, basically the statement of superdense coding, which I'm guessing that most of you will have heard about before. But as we shall see later, this ratio can actually be much, much larger than just 2. It can also just be 1, so channels where there's no boost, for example, this completely dephasing channel. And there are also channels where both capacities can be 0, so technically the ratio is not defined there. That's fine, because the capacity is the 0 if and only if you have a replacer channel, so a channel that destroys all information. And if the classical capacity is 0, then luckily the entanglement assisted capacity also has to be 0, which you can kind of see as the statement that you cannot communicate only by use of entanglement, at least not without breaking special relativity or something. Okay, so let's look at some more complicated channels. For example, the qubit depolarizing channel. This becomes a replacer channel when this depolarizing parameter p equals 1. So we know that both capacities vanish at this point. So what exactly happens here? Do the ratio blow up, or does something else happen? Well, the answer is the ratio converges to 3. You can see the graphs of the capacities and ratios here. So nothing really special happens, even though both entanglement assisted and classical capacity is 0 here. But maybe this is just like a lucky or special channel where nothing really happens. So there are other examples, for example, the amplitude damping channel, where now we have a figure of the ratio between entanglement assisted capacity, and now instead of the classical capacity, we have the CH. You can just think of that as the classical capacity for the moment. This will actually be an upper bound on the real ratio of capacities, but if you just look at this figure, it's kind of hard to tell, does this ratio blow up, or does it converge to something, or what exactly happens? Well, the answer is that it does converges to 4, but the convergence happens extremely slowly. Like if p is 10 to the minus 50 close to 1, the ratio is still only 3.8, so it's really hard to tell in general what happens to this ratio and to say something general about it. This also indicates that perhaps like the derivative of this ratio is unbounded. And finally, so as far as we know, the channel with the largest known ratio of capacities in fixed dimension is this oversaturated depolarizing channel. So the depolarizing channel where the parameter is as large as possible. And for these channels, the ratio of entanglement-assisted and ordinary classical capacity is somewhere around a little bit more than 2D. So this, for example, shows that the ratio can get arbitrarily large if we let D get arbitrarily large. Okay, so let's return to the question of the talk. Can the ratio CE over C get arbitrarily large? Well, yes, we just saw that it could for this oversaturated depolarizing channel. But it only gets arbitrarily large when the dimension gets arbitrarily large. And in fact, for all known families of channels where this ratio can be calculated, the ratio is always upper bounded by some linear function of dimension. And with this quick survey of the landscape, it's no wonder that Bennett, Shor, Smolin, and Taplial, in a very famous paper from 2002 about entanglement-assistant, conjectured that in the setting of fixed channel dimensions, this ratio should be bounded. And this is what we're going to solve now, because this has now been resolved by our work, which actually derives an upper bound on this ratio that depends on input dimension. So the work, which I'll get more into later, entails that you get a bound like this, where the entanglement-assisted capacity is upper bounded by some order d squared over log d function of input dimension times the classical capacity. Okay. And briefly, it's worth mentioning that since we have these trivial bounds on the capacities, which are tied for the identity channel, so the ratio can only get arbitrarily large if the classical capacity goes to 0, so in the vicinity of replacer channels, or channels with small capacity. But it would be conceivable that you could have examples where, for example, for some parameter family of channels, the classical capacity converges to 0 much slower or much faster than the entanglement-assisted capacity, which would make the ratio blow up still. But this, as we'll show, cannot actually happen. And I'll also just briefly mention some motivation. So of course, the original motivation for our work was to solve this conjecture by Bennett and Shor, Smolin, and Tapial. But actually, people have also investigated this ratio for practical applications. It remains mostly speculative now, granted, but for example, in deep space communication and covert communication, it has applications to try to answer how large can this ratio be for really noisy channels. So that's channels where the capacities are very small. Okay, so without further ado, I'll present our main theorem, which, as I said, is a new bound on CE over C. And it is precisely this bound. So the entanglement-assisted capacity of T is upper bounded by this complicated function of input dimension dA of your channel times the classical capacity. And just for context, so for example, if we restrict ourselves to channels with a qubit input, this bound tells us that the ratio is upper bounded by 14.23, which in comparison for this oversaturated depolarizing channel is around 5. So there's still about a factor of 3 room for improvement if you want a tight bound. And this function scales as 8 d squared over log d for large d. And further, the classical capacity can be replaced by this ch I mentioned before, which is actually a lower bound for C, thus proving a slightly stronger result. Okay, so that's our main theorem. Now I'll briefly run through the proof, maybe not too briefly, but I'll skip some steps and otherwise try to give you the main idea behind the proof of this theorem. So firstly, I don't know if you remember the expressions for the capacities I explained before, but if you don't worry, we won't actually use these kind of limit expressions. We'll make use of some previously derived expressions for these capacities. Unfortunately, there's not really a nice expression for the classical capacity. The sort of best thing we can do is like this regularization expression in terms of this CH, which is usually called the Holevo quantity or Holevo capacity, which is the supremum of all convex combinations of quantum states, where you take the entropy of the convex combination, then minus the same expression where you put H, so the von Neumann entropy inside the combination. And since this quantity is subadditive, this shows by the theorem here that CH is a lower bound of C. So from now on, we only have to worry about CH and CE. We don't need to discuss the classical capacity anymore. And weirdly enough, even though the classical capacity cannot be expressed nicely, the entanglement-assisted capacity with like a more complicated definition does indeed have this single letter kind of simple formula, which was proven by this, or in this paper I also mentioned before, by Bennett, Shore, Smolin, and Taplial, which I'll also reference a couple of times more in this talk. So this characterization states that the entanglement-assisted capacity is the largest mutual information you can get between some auxiliary system and the output system of your channel, where your state is identity tensor your channel, acting on some purification over the input states that you maximize over. And the mutual information is over bipartite state is the individual von Neumann entropies of the subsystems minus the total von Neumann entropy, which is defined here. Okay, so by fiddling around with these expressions, we can actually get CE and CH on these kind of similar forms. The only difference is this auxiliary system. If this A prime, for example, had dimension 1, then we would be done by now because these two expressions would be equal. But of course, they're not equal. So our task will be to we'll try to sort of trace out, in a sense, this auxiliary system A prime from the expression for the entanglement-assisted capacity, and then incur some penalty in terms of some dimensional factors. D rho sigma here is the relative quantum entropy defined here. So this is kind of the same thing as the diamond norm of an operator is upper bounded by dimension times the one norm. It just like now we want to do the same thing for these quantum relative entropies. Okay, so now I'll get into some more technical details, but bear with me. So we start with the expression by Bennett and others, and then by some elementary entropy inequalities, we arrive at this upper bound. The proof will just be a series of upper bounds, and then in the end get the upper bound that we need. But we can replace our output state with this weird combination of the image state we want, but also the image of the maximally mixed state. And there will be a good reason for choosing this later, but it's not really obvious why we choose this state right now. And since this purification that we maximize over is pure, we can do a Schmidt decomposition and introduce these coefficients alpha and write down our state 5 rho as a bracket of V. Okay, so now we sort of reach the main idea behind the proof. So it turns out that you can prove these lower and upper bounds of the relative entropy in terms of these quadratic forms, the quadratic forms K of the input in the parentheses, which looks pretty weird. They have this integral definition and also this sum definition, kind of similar to the Fisher information in terms of, now we just have this slightly different coefficients of the eigenvalues, sigma, which can get arbitrarily large. But it is really nothing more than a sort of second order expansion of the relative entropy around the points where your two states are almost equal, with some caveats. Like here we always assume that all your operators are full rank, and there are some problems with that I explained in our paper, but you can get around these things. And here you also keep a sigma constant. This is basically the idea. So the lower bound also involves k, but also this weird function g of k. But as long as we make this k only dependent dimension, or as long as we can bound this k, which is the minimal number, you have to multiply sigma to get something strictly larger than rho in semi-definite order. We can sort of change back and forth between working with k and working with relative entropy. And this quadratic form will have some nice property when you want to trace out this auxiliary system. Okay, so relevant states can be written like this by using the Schmidt decomposition. And by the definition of k, we get this complicated expression where alphas are the eigenvalues of the auxiliary reduced state, and s are the eigenvalues of our sigma that we chose before. We now have to find this linear map delta t as the difference of t with replacer channel sigma b. And the thing we want to do now is separate the s's from the alphas in this expression. This will sort of trace out, as I kind of alluded to, this auxiliary system. In a way, of course, scarecrows around everything. And this works because the logarithm is a concave function. So this log x minus log y divided by x minus y is really the slope of the line connecting 2 points on the graph of the logarithmic function. So you can replace alphas, all the alphas in this expression, by just the minimal value of the two and still get an upper bound due to concavity. And when we do this and do some other manipulations and a little bit of linear algebra, so we need to, for example, introduce these chi states to make everything make sense. In the end, we arrived at this expression, which is nice because now we have k of something that only lives on the output system of our channel. So we're actually almost there because the only way that this expression depends on the auxiliary system is only through these alpha coefficients, which in the end will just get summed out. And now it was important that we chose our state in this way, because due to this mixture with the maximum mixed state, if we multiply 2 input dimension minus 3 halves by sigma b, we get something larger than any output state in semi-definite order. So now we can actually use this lower bound for the quantum relative entropy I talked about before, and only incur penalty by this g of k function of k, which is something finite. And we have returned to an expression only containing relative entropies. So that's nice. So the last thing that's left to do is just play a little bit around with this expression. For example, we now see why we chose sigma b to have this weird form. And this is exactly because by Donald's identity, sigma of b will actually be the unique minimizer of this expression. So now we can replace sigma b by an infimum over states, or just by an arbitrary state, still get an upper bound. And we can also do supremums over the other states in our quantum relative entropies and still get upper bounds. And we end by all the alpha coefficients just summing, getting separated by a sum, which sums to 2k. And we have this expression in the end, which, if you recall, was one way to characterize the whole level quantity of our channel, which is exactly what we get here. So putting everything together by using this expression for the entanglement-assisted entropy that Bennett writes and others, and using all the inequalities just mentioned here before, we end up with the result. And that's basically it. of course, there was something that were brushed over in the proof that you can read about in the paper if you want. So we're left with some open questions. Like the real open question is really just like, how can we improve this bound? Let's be some more specific ways of investigating this would be either to say, does there exist just a linear function dimension that actually upper bounds this ratio? By the bound just proven here, we know that ratio is maximally in between some linear function and some d squared over log d function. But can we actually prove something that's tight? Or maybe find some quantum channels where the ratio is more than linear. Also, like so far, we've only talked about input dimensions, but does there also exist a bound that only depends on output dimension? That would also be a good question. There's also like, besides all the applications I talked about before and solving this conjecture by Bennett, Shores, Moulin, and Tablial, there's also this like direct application that follows from the new result. So heard a lot about error correction. So like in actual physical systems, there's some gate noise associated with using a channel many times and encoders and decoders. This motivates this fault-tolerant entanglement-assisted capacity. And there's been this question about whether one can prove a channel-independent continuity bound. And this difference to the zero error entanglement-assisted capacity. And this actually gets answered automatically by this upper bound on CE over C proved here due to some earlier proven inequality for this fault-tolerant entanglement-assisted capacity. So now we can just replace this by some dimensional factors. And if you want to hear more about fault-tolerant entanglement-assisted capacity and like realistic communication scenarios, you can listen to Ashutosh's talks on Friday. He will talk a little bit about this. Oh, that's it. Thank you for coming to my talk.
Thank you. Questions? There's one here and here.
Hi, thanks for the nice talk. I was wondering if you tried very hard to look for an example where the ratio scales like d squared.
Yes, we did,
Okay.
but couldn't find any. But you know, like the upper bound proven here scaled like d squared divided by log d. So it's actually impossible to find channels where it scales exactly like d squared.
Right.
But like, just try to find anything that scales like faster than linear and d, but couldn't really do it so far. But I would guess that it is actually like the case that you cannot scale faster than linearly and d. Like there probably exists an upper bound that is just linear and d, but which is just really difficult to prove. I mean, even more difficult than this result.
Do you think you lost something in the second order Taylor expansion? Sorry for the follow-up.
Yes, actually, that's like I'm pretty sure that that's where the factor was lost. I can just return to this. So there was like one step where we gained a DEA, which was towards the end by like we used this Donald's identity and stuff. And there was one step where we lost approximately a d divided by log d. And the d divided by log d was again by using this entropy inequality. And of course we know that we have to gain a factor of d in total because the ratio can be lower bounded by d. So we need to get above d. So we cannot just, so if the other factor of d was removed, then we would get something that like an upper bound, which would just be d divided by log d. And that cannot happen. So this sort of indicates that the sort of the factor that was like the annoying factor was kind of lost here.
All right, thanks a lot.
Yeah, thanks for the question.
Hi, thanks for the nice talk. I was wondering if what's the landscape like for other kind of capacities? So I guess for private versus quantum, this ratio can go to infinity or something? Is there like these some special rocket type constructions where this blows up, or do you know if there's similar conjectures for other ratios?
I don't really know too much about the private capacities and stuff like that, but at least for the quantum capacities, which are pretty similar to the classical capacity, except now just measure like how many qubits you can send through a channel instead of classical bits. There are the examples of channels with like 0 quantum capacity, but with non-zero entanglement-assisted quantum capacity. So for these, for the quantum capacities, there certainly doesn't exist an upper bound like this.
Mm-hmm. And like for the feedback assisted, like for the entanglement assisted, like these two capacities, if you allow like classical feedback or like two-way LOCC assistance, is there anything non-trivial that can be said there?
I don't really know. I haven't looked too much into that.
Okay, yeah,
But
just
could be interested to, I'll obviously be interesting to see like whether you could use these techniques to prove other things. Since
Okay.
they are like, I think you can express a lot of things in terms of these relative entropies. And basically all we've proven here is like a series of inequalities involving quantum relative entropies.
thank you.
Yes. Okay. Eric or Kun?
Thank you for the talk. So my question is, do you think these techniques could be used in the case where you want to bound the dimension of your entanglement?
So with that kind of corresponds to like this auxiliary system having bounded
Right.
dimension, you think?
Exactly, yeah.
Yeah, I think so. Like, I think that would lead to strictly better bounds. Because this dA, at least at one point, comes into the proof as like the rank of your Schmidt decomposition.
Mm.
I guess maybe if you require that this that the auxiliary system has bounded dimension, then at least here you can like take the minimum of dA and this dimension, and maybe also like the other place where the dimensional factors come in. But I'm not really entirely sure about how this dimension of this auxiliary space in like a Bennett and others formula for the entanglement assist capacity relates. If that is the same thing as the as a dimension of the space of whatever entangled state you use for your actual communication protocol. I mean, it might be the same, but I'm not really just sure. But possibly.
Thanks. Very interesting results. So I basically have this almost the same question as Eric. So the entanglement assist capacity, like so in this capacity, it might use infinite number of the entanglement to achieve the optimal rate, right?
Yeah.
So the capability of such a rate is contributed by two factors. One is that you use quantum channel. The other factor is that you use entanglement
Yeah.
state. So is it possible that you have a more fine-grained analysis, like so a bound that's related to the channel capacity and also the entanglement state that you use? Right. So this can be a sort of chain rule properties for capacities.
Yeah, I guess maybe.
Because now
Could be
your
possible.
upper bound is only depend on the dimension of your channel, right? So
Yeah.
there's nothing entanglement there. So I was wondering if it's possible to have a more fine-grained analysis.
Yeah, again, I'm not really sure how the dimension of these spaces from a Bennett's formula relate to sort of structures of your communication protocol. But I mean, surely, like when you have unbounded everything as you have for this entanglement assist capacity, like the upper bound proven here will also work for all the other sort of, if you put restrictions on and everything else. And I think this like a Olevo quantity, CH, is kind of related to, or is basically the classical capacity where you sort of restrict to product states amount, between users of your channel. Not entirely sure, but so that kind of corresponds to some single shot, or not really a single shot capacity, but something like that. So since like all dimensions are sort of unbounded in our CE expression, and this CH only kind of, that is sort of kind of related to just using your channel one time. I would sort of guess that it doesn't really matter too much, like if you put like further constraints on dimensions or uses of different stuff. I don't know if that answers your question, but
Oh, okay, yeah, and maybe we could talk later. Yes.
Okay. Maybe we should wrap up, but maybe one very quick wrap up. Okay, you can ask it offline. Okay, thanks a lot. Thanks to all the speakers.